not part add to stream. Hey, you 11s. Okay, so I'm really sorry that I haven't been able to do this sooner. It's just all been a bit chaotic with Christmas, but I know that we need to finish off paper 1. So today we're just gonna box off 2019 June's paper, and just to make sure that everybody has finished paper 1. I kind of hope that the delay in me finishing this paper has meant that you've had a bit of time to review what I've already done. And I'm just going to check that you guys are able, yeah, you guys are able to see me. That's great. I'm just going to see whether or not I can make that so it doesn't steal any of my bandwidth. Okay. Right. So I'm just going to finish off the paper. I'm not going to faff around. I'm just going to continue where we left off. So if I go share screen, if I can do this, if I go that one and go share screen, let's box this one off. Okie dokie. Should be switching over. Let's hide that, drop that down there. Okay, and then on to our paper. Sorry, just fiddling around with power cables since I've moved over to my cable. Right. I don't need, I'm going to get rid of that. There we go. And onto my paper. Yay. Okay. Give me a message. I know that I'm just going to send a message on the chat when someone's here. And you guys can just let me know that you can hear me all okay. Okay, so we left off on the paper at enthalpy change, and we were making really good progress. We were discussing all the various pros and cons that went with enthalpy change and all the problems that came with them. And we're now moving on to rates of reaction. So question 13, a student uses this apparatus to investigate the rate of reaction between a magnesium and an excess of dilute hydrochloric acid. Now that is already, it's nice for me to just point that out. They have already emphasized this word excess, and of course we all know that that means too much. They've added more than enough. So I'm assuming that there's going to be a question that relates back to that. The second thing for me to point out is this practical. So they're using a gas syringe here, and this is a diagram that every now and again at GCSE, this diagram is asked for you guys to draw. And I just want to emphasize the gas syringe. I want to emphasize that it has a scale, these lines here, just to make sure that when you draw it, you don't need to be Picasso. You can draw a very basic version of this. And it's just to remember that scale. It's one of the most commonly lost marks for this practical. Another thing that this practical often lends itself to are problems in setup. You often see interesting points where they draw a bung which is too small. And they'll draw a bung like this, and there'll be a gap. There'll be a gap between the bung and the conical flask, which will be there. And so what this means is any gas produced would escape through that gap. And they often ask this, and they show a diagram which is incorrect, and they'll say, looking at the diagram, try and identify any problems and identify what this would do to our reading. And so what you identify is there's a gap between the bung doesn't fit the conical flask, and that gas would escape through this gas, meaning that you would get a smaller reading. So it's a very common one in terms of practical faults. Okay. So the next thing I then said is she uses this method, and they then describe the method. So I'm just going to see if I can make this work. There we go. So it uses a graduated beaker. That's interesting. By the way, they are doing that. They're throwing in the word graduated there just to freak you out, year 11. The word graduated simply means it has markings that show volumes. So if you had a beaker, a flat out normal beaker, and beakers do have markings on them, but a graduated beaker would be one that has markings that have been specific for volume. So these aren't just labels that are rough. It tends to mean that they're actually pretty decent. So the word graduated means that it has a scale on it. graduated. Now, you guys come across this, of course, in graduated pipette. And a graduated pipette is simply a pipette. Now, most of the time, it's a large body pipette, so it looks a bit like this. It's a rather odd device. Used in titrations, of course. Sorry for the terrible diagram. And a graduated pipette has one marking on it, which is usually going to be 25 centimeters cubed. But that marking is done accurately, hence the graduated. So nice to see that word making an appearance. Try not to freak out about it. She adds the piece of magnesium ribbon, and she adds 0.086 grams to the acid and puts the bung in the neck. She measures the volume of gas collected every 10 minutes until the reaction stops. The reaction shows the student's results. Okay, so plot the student's results on the grid, 1 mark, draw a line of best fit. So quite nice this, because usually this is worth 3, but in this case it's only worth 2. Edexcel finally wising up there and realizing that they're giving out marks where they shouldn't do. Now I just want to show you what I've done here, which is I've taken the data from the previous page because I've got a tablet and I can do that. I've taken the data from the page and I've put the data next door to make this easier for me to plot. So let's plot our data. So at 0, by the way, this is the most common fault for students. The first bit of data, students think that that is not a data point, but it is. You must include that data point on your graph. Please make sure you do so. So at 0, it's at 0 time, it's 0 centimeters cubed of hydrogen. At 10 minutes, it's going to be 29. So take the time to figure out what the scale is. So this is 30. So that means that each one of these is 2. So at that point, 29 is going to be right in the middle. And make sure you spend the time on getting this right. It's so easy to throw these marks away, and students do on a regular basis. So at 10, it's 29. At 20, it's 52. So 52 is there, hence that one being 50, and it goes up by 2s. Next, we then have at 30, it's 67. So at 30, it's 60. Well, that's interesting. So 65 is right in the middle. 66, there you go, 67. And then 76 at 40. So there's 70. 76 will be then here. Next, 81 is at 50. So at 50, it's 81. So that's right in the middle there. And then 84 at 60. Just checking that. There you go. And then 84, 84, 84. So now the reaction has stopped. Right. So then we've got 1 mark. Please, in your GCSE, take 30 seconds to check your plots. They're going to be doing it. Every one of your plots will be checked. I'm just going to check that you can hear me. Excellent. So that's all working perfectly. That's great. So, okay, now they want me to draw a line of best fit. Now, lines of best fit, year 11, you know exactly the trouble here. If you decide to do your line like this, the artists in the room, if you decide to do this, your artists like to do furry lines, you will lose it. That is 110 lines of best fit. Please don't do it. You get 1 shot at this, folks. 1 shot. So take your time, line it up, get it right. So you turn the page to fit. Turn the page to fit the curve of your wrist. Oh, I've taken off too many points. There we go. Let's put them back on. I'm just putting the points back on. I skipped too far. My tablet being a bit slow. So I've turned my tablet, just like you will in your exam with the page. I have turned the tablet to fit the curve of my wrist. So let's see if I can do this in one go. I'm going to do this in red. There we go. It's okay. Turn the tablet so it matches the curve of my wrist. It's a bit awkward with that tail at the end. Oh, there we go. And they will definitely, even just to let you know, and it's nice to talk this through, even with that wobble, they're going to give me it. That wobble tells the examiner that you did this freehand, that you did it the way it was meant to be done. My hand got stuck on the tablet. It's a little bit less, it's not quite as easy as compared to paper, the way that your hand moves a little bit easier. Tempted to give that another go. But in reality, I'm going to, again, I'm practicing the curve. Let's try that again. There we go. Better. I came off the page because I wasn't pressing hard enough on my tablet, but you can see that that line was much better the second time. And you must do this in one go. You've got to, year 11. Please trust me on that one. It's only worth 1 mark, but you've got to make sure you've practiced those. Okay, next. Okay, so the student now repeats the experiment using, oh, look, he has halved the amount of magnesium, but he has kept the hydrochloric acid the same. So the hydrochloric acid is still in massive excess, but he has halved the amount of magnesium. Now look at the lines. So we can see that this graph ended at the 84. What that means is if I halve the magnesium, I'm going to halve the amount of hydrogen I produced. So that's going to produce 42. So I'm going to mark 42 here. It says, draw on the grid the curve that you would expect from this experiment. The next thing is, where did the original experiment end? The original experiment ended here. Now, he hasn't changed the concentration. Remember the 5 factors that alter rates. We have concentration, we have temperature, we have surface area, we have catalyst, and we have pressure in gases only. So this one, does it tick any of those boxes? The concentration remains the same. The temperature hasn't changed. The only thing they've changed is the mass of magnesium. What that means is the rate's going to be exactly the same. It's going to be the same. So it's going to end in the same amount of time, which is here. So I now need to produce half that much. Oh, and here's the next tricky bit. The rate is also going to be the same at the beginning. So I'm going to do this in a different color now. Because I haven't altered any of these things, all he's changed is the mass of magnesium. The rate at the start will be the same, which means I'm going to follow that line. I'm going to zoom in on this. I'm going to follow that line. So I'm going to follow it up. And it doesn't matter actually how far I follow it. As long as I follow it for a period of time. Now I'm going to curve off and end at exactly the same amount of time. So that is the curve they're expecting to see. They're expecting to see you understand that you haven't altered any of my 5. The rate at the beginning will be the same, but it's going to start to slow down and produce half the volume of hydrogen gas. Next. Right, this time he's gone back to the original mass of magnesium ribbon. He has kept the same concentration and volume of acid, but this time he's done it at a slightly higher temperature. Right, so he's gone back to the original line. He's going to produce the same volume of hydrogen. He's going to be going at a faster rate because he increased temperature. So, but I need to end earlier. But hit the same volume and be steeper. So I'm going to switch this now to blue or purple. I'll go for blue. Right, so I need to go up steeper. Oh, I'm going to try and do that again. And I'm done. So I've gone up at a steeper angle. That's the temperature's impact. It's going to increase the rate of reaction. And we recognize that the rate of reaction is we only tend to measure it at the initial rate because it's easiest to do so at that point. We can measure the rate at any point, by the way, by taking a tangent and then making sure that it's even on either side, which it isn't really. I've got more on that side than that side. That's not a good tangent. But we make it even on either side. Still not particularly good. Just get rid of those. Well, darn it. There we go. But I'm hoping that you understand what I'm doing at this point. If you ever take a tangent, you then get your delta x and delta y. And then you just do y over x. So it's nice just to mention gradients. I'm assuming they're not going to do that here. Curve z. Okay. Now look at the marks. Talk about a great question. You have 2 marks for each of those lines. And 2 marks for each, considering the lines don't take you long, but it's a very easy line to make a mistake on. Please consider the process I went through. I decided whether or not it was going to produce the same amount of hydrogen. I decided whether or not it was going to be steeper. I decided whether or not it's going to end earlier, and then I drew my line as needed. So do bear that in mind. Next. Okay, the expected volume of gas produced in the first experiment is 86. Suggests by the volume is collected is less than expected. Now, there are loads of answers for this. However, there are a few that are top. So I'm going to list all of them, and then we'll and I'm going to hopefully try and do them in order of importance here. So the first one, I'm going to say gas lost when bung being fitted. Now, what I mean by that is they're going to add the metal to the acid, and there's going to be a delay between them adding the metal and putting the bung on, which means some gas is going to escape. We're going to lose a bit. The next answer, I'm going to go over here. So number 1, loss of H2 during time between adding magnesium, between adding Mg to acid to, was it HCl? Yeah, it was. To HCl and bung being fitted. Second one, gases are soluble. Some H2 will be dissolved into the water. Now, can I just point out, I actually don't like this. Hydrogen has a very low solubility, so it's not a great answer, but it will be allowed. The next thing is impurities in magnesium. Notice I haven't said in the HCl, although technically you could probably say that as well, but the magnesium is more important in that setting. The next one is maybe the reaction hadn't finished. We know that the reaction itself slows down massively at the end because the concentration of acid decreases. Well, maybe this was actually at a slight angle and it was going to take an hour for the last 4 centimeters to be produced. So incomplete, maybe the reaction hadn't finished. So incomplete reaction. All really good answers. I'm pretty sure they'd accept most. But if they said give the top reason, it would probably be lost during bung being fitted. Okay, next. The student used a graduated beaker. Ooh, that's funky. Graduated beaker to measure the volume of dilute hydrochloric acid. Explain why it is not necessary for him to use a measuring cylinder. Right. The reason for that was because the acid was in excess. The acid was in excess, which means we didn't have to add it. We didn't have to add it in a precise amount. We just needed to make sure that there was too much. So we don't really need to measure it. We just go, I need 18, so let's just add roughly 25. It doesn't matter that I'm going to be above or below it by a little bit. Acid was in excess, so exact volume, exact vol doesn't matter. Doesn't matter and won't affect. So won't affect vol of H2. Sorry about that too. Volume of H2. Next, the ionic equation for the reaction between magnesium and hydrochloric acid is as followed. Use the information in the equation and the particle collision theory, information in the equation, particle theory to explain why the rate decreases. Right. So we are running kick-ass. That's what we know we're running. This is the K stands for knowledge. That's your particle theory. This is your knowledge. And then your knowledge is always regarding P theory, particle theory. Next, we need to talk about the number of collisions. Next, we need to talk about activation, the number of particles with activation energy. Oh, don't need to do that one because it's not the only time that matters is temperature, technically, and a catalyst as well. And then the last thing is successful collisions. And then, of course, rate. Right. So the rate decreases. It's already done for us, which is nice. So knowledge. I'm going to change my color now since I've written all over it. Okay. So as the reaction proceeds, what's happening? The acid is going to get used up. So as reaction happens, as reaction proceeds, the HCl is used up. Therefore, its concentration of HCl decreases. And there is the one from the 5. Students often ask me at this stage, they often ask me, why is the magnesium being used up? Why does that not matter? The reason being is the mass of magnesium is not going to change. It's not one of our 5. However, the acid will alter its surface area slightly, but it's actually not going to change it all that much. The big thing that's going to happen here is the reaction slows down because the concentration of the acid drops. Next, if the concentration of the acid drops, we need to explain what that is. Fewer particles, fewer HCl, it's nice to be really accurate here, fewer HCl particles per unit vol. So per unit vol, we're explaining what concentration is. Therefore, fewer collisions, because if there are fewer particles, they're going to collide less frequently. Or by the way, you can say collision frequency decreases. Fewer collisions will occur, therefore, fewer successful collisions. Fewer successful collisions. And there's your answer, and I'm done. Next, okay, a salt can be made by reacting an acid with an insoluble base. Ooh. A student has a sample of copper oxide. That's black, by the way. You've got to know that. You've got to know that one, year 11. Copper oxide is black. Just to now give you some others that you need to know, which is always nice. Copper carbonate is blue-green. Just to let you know, by the way, that's actually turquoise, and it really annoys me that they don't allow it anymore. They want you to say blue-green from Edexcel. Really annoys me. Copper carbonate is blue-green. Copper sulfate, on the other hand, CuSO4, if it is hydrated, so CuSO4.5H2O, that's blue. That one is blue, but anhydrous copper sulfate, CuSO4 anhydrous, meaning no water, is white. It's also the test for water, just so you know. It's nice just to mention it. So it says, the student pours 50 centimeters of dilute sulfuric acid into a beaker. She warms the acid with a Bunsen burner. She adds a small amount of the copper oxide to the warm acid and stirs the mixture. She adds a further amount of copper oxide until copper 2 oxide is in excess. Filter the mixture and obtain the crystals. Wow. It was going super well until the last bullet point. That last bullet point was just like, wow, you've seriously rushed that. Okay, state why the acid is warmed. Provide activation energy. If chemists, just to let you know, by the way, I'd love to look at the mark scheme for this, because provide activation energy. You could also say to increase the rate of reaction. Why do we heat anything? Increase rate of reaction. it's very easy for students to forget that in reality, we're on a deadline here as chemists. We're trying to make stuff. We want to make it as quick as possible. We heat everything. We heat everything because we want it to go quicker. And if we are doing this in an hour, and by the way, we despise solids. Solids are so boring. They're slow. You've got to powder them. If you don't powder them, use granules. It's even more of a nightmare. So we're trying to make it as fast as possible, considering we've got a solid. State how the student would know that the copper oxide is in excess. Right. So when she adds the first amount of copper oxide, she starts off with sulfuric acid. And the sulfuric acid, of course, is aqueous. H2SO4 brackets AQ. And she's going to add solid black copper oxide. Now, what's going to happen is it's going to react with the sulfuric acid and it's going to become copper sulfate. And the water is going to turn blue, which is always fun. Kids love that. It's nice. It turns blue. And the black copper oxide will have vanished. It started here and it's now gone. So how do you know when it's in excess? You keep adding it until the reaction no longer makes the solid disappear. So, by the way, that actually is very interesting because at A level, just a drop in the A level bit here, how would you know that the reaction had ended? Well, there's no bubbles here. It's going to get darker blue. You'd probably want to monitor the pH in reality. You'd monitor the pH, and the pH, of course, will drop because the copper oxide is acting as a base. It is going to neutralize the sulfuric acid. The sulfuric acid is going to be down there at pH 1. And then when you add the base, it's going to react with the acid, and it's going to form copper sulfate and water, and H2O. And your acid, the pH is therefore going to increase. Just to show you like, graph looks like this. And the neutral point is right in the middle. It's a rather odd graph when you neutralize acids. You get this sudden transition step where the acid is suddenly gets to neutral, and you get this skyrocket of alkalinity. The pH suddenly increases up to being out. But in this case, we've added a base, not an alkali. So our graph wouldn't actually look like that. We're still going to have it increase. We're still going to have a jump, but then it's going to get to 7, and then it's going to tail off. So that's going to be 7, that is. Because we're forming salt and water, that's going to be 7. We're not becoming alkali because when that's a base, that's an insoluble base, and it's not going to be making it alkali at the end. It'd be a rather interesting graph. That's a bit far, to be honest, for you at GCSE. But how do you know the copper oxide is in excess? I'm going to say you're going to add it until the black solid stops disappearing and remains after a long period of time. Black solid, black CuO remains after reaction has stopped. Now, people are going to say, how do you know the reaction after reaction has stopped? How do you know the reaction has stopped? And I just say, you don't. You're just going to say, example, a long period of time. A long period of time. It's going to still be there. I'd like to see the mark scheme for that one and mark the rest of them. I wonder if I can actually track down my mark scheme at this point. I don't know if I can. My laptop is already starting to... Oh, I don't know where the mark scheme... I haven't got the mark scheme up. Oh, I'll have to check that. I'll get that up towards the end. Next, state why the mixture is filtered in stage 5. It's to remove the excess copper oxide. You've got a black solid floating around. Remove the excess CuO. State the color of the filtrate. Right. The filtrate is the liquid that passes through the filter paper. This is common. By the way, filtrate, straight out of year 7. Filter paper. You filter your solution, the black solid will get caught in the filter paper, and your blue liquid is going to come out beautifully blue with no solid left behind, and that's your filtrate. The sediment will be left up. Is that technically true? No. But the filtrate is the liquid anyway. Filtrate. And so the filtrate is going to be now blue. It went from colorless sulfuric acid to being blue copper sulfate solution. So that's going to be a blue solution. Blue sol. Next, describe how the student could obtain a pure, dry sample of hydrated copper sulfate in the crystals. Right. We know that this is a 6 marker. It's a big, long set of bullet points. I still have nobody here watching this webinar, and I wonder whether or not it's either because none of you are here or because I'm not streaming correctly. Anyway, we will continue. So now that we have a beaker of just copper sulfate solution, CuSO4 aqueous, and it's a beautiful blue. No solid's already gone. Right, and we want hydrated, not anhydrous. We don't want to get rid of all the water. We want to get rid of most of it, but not all. So step number 1, you're going to pour solution into evaporating dish. Let's draw the picture. Tripod, pipe clay triangle, evaporating dish, and there's your solution, and you're going to have heat, and that there is called a pipe clay triangle. Again, a common equipment that students forget the name of, and also of course an evap dish, and I'm going to spell that differently actually because I shouldn't have spelled that evaporating dish. Right. Now we're going to heat it. Heat until 80% of the water has disappeared into the air. Disappeared. Right. Next, we're going to use a glass rod. To see if crystals form. This proves saturation, just so you know. Proving saturated solution. Right. Now we're going to let it cool. Let it cool so crystals form. The water will continue to evaporate and those crystals will suddenly start to come together. And that last 20% of the water will be trapped inside the crystal, hence hydrated. The crystals are therefore going to be blue, not white. If it said anhydrous, we're just going to evaporate it till nearly all the water's gone, and then we're going to heat it until dryness. But in this case, we're going to let it cool so crystals form. And then we're going to leave in warm place to dry. Now it says pure and dry. So it's interesting that I say pure. That's going to get you all the marks there at this point. But leave it in a warm place. Maybe, let's say, pat down with, I don't know, tissue paper. You don't want tissue paper, you just want paper. With, what would I use? I'd probably just use tissue paper. Yeah, tissue paper. To remove any last bits of water. And we're done. I'll check the mark scheme again at the end. I will try and find that. I can't actually remember exactly what I've done with that, which is a bit frustrating because I thought I had included it on the webinar, and I clearly haven't. It's rather frustrating because it's going to be tricky for me to track that down though. It's going to be in my downloads probably. I thought I'd tacked it on the end. See if I can go to my downloads and see if I really, you know what? It's whenever I'm doing, where would it be? It should be in here. But whether or not I'm going to find it or not is a bit different. Can't find it. Come back to it. Okay. Go back to this. I still have nobody watching. Worries me. Okie dokie. Go back. We're nearly done, folks. Right, we're into calculations. Right. The overall equation for the formation of hydrated copper sulfate crystals from copper oxide is shown below. In an experiment, a student reacted, this is nice, so we're straight into calculations, 9.54 grams of copper oxide. I'm just going to write that over the top. 9.54 grams. Probably going to drop me into grams over rams. Show in the experiment, show that the maximum possible mass of copper sulfate 5H2O's crystals can be obtained as 30 grams. And they've given us the MRs. Isn't that nice of them? Right. What is the ratio? So first thing I'm going to do is number of moles is grams over rams. Now I have got the grams of copper oxide. So number of moles of copper oxide is going to be 9.54 over the MR of copper oxide, 79.5. Answer. Calculator, never going to do those things in my head. 9.54 divided by 79.5. Answer. 0.12 moles of copper oxide. Next, the ratio from the equation is a 1 to 1. So the moles of copper sulfate hydrated is going to be exactly the same. Wait for a minute. Right. Ratio is 1 to 1. Right. Therefore, I am going to get moles of CuSO4.5H2O is going to equal exactly the same number, 0.12. Right. Now I need to work out the mass. I need to rearrange grams over rams. Bring the rams over. Number of moles times by the rams will give me grams. Right, input my data. 0.12 multiplied by the MR, which is 249.5, giving us all the data, times, it's even on my calculator still, 249.5, and I get 29.94 grams. And that mark is worth 1. Don't round to 30 straight away. Therefore, the mass is 30 grams because it gets rounded. Does it says give your answer to the appropriate number of significant figures? Well, in that case, it's 3. I would actually leave that one exactly the way it is and then go 30.0. It rounds. We're good. Next. In this experiment, the actual yield of copper sulfate crystals is 23.92. Calculate the percentage yield. Right, percentage yield is the actual yield over theoretical yield times 100. So let's put in that data. Actual was 23.92 over 29.94. I'm going to use the real number times 100. 23.92 divided by answer times 100, and I get 79.9%. And I'm done. Nice one. Next. Hydrated ammonium iron 3 sulfate is a violet solid that has the formula. Oh, good grief, that's horrible. The table shows some tests done on 3 separate samples. Wowza. So, dissolve the solid in water and add acidified barium sulfate. They're testing for the sulfate ion. You've got to know your chemical tests here, 11. Right, does it have it in it? Oh my goodness, it's got loads of them. So, observation, white, precipitate will form. of barium sulfate, which is a white solid. And that's because it contains sulfate ions, and we are testing for sulfates with barium chloride. Next one, dissolve the solid in water and add some sodium hydroxide. Right, what's sodium hydroxide the test for? The sodium hydroxide is testing for iron 2+, iron 3+, and copper 2+. So we add sodium hydroxide, and am I going to see it? Yes, I am. It contains iron 3. So I'm going to form a brown precipitate. Precipitate will form. You've got to know your tests. You can't make this stuff up. And that's going to be, of course, Fe brackets OH brackets 3 solid. Iron 3 hydroxide, which is brown. Iron 2 is green. Right, the next thing is they add some sodium hydroxide and warm the mixture. Test the gas given off with the paper. Right, so now they're testing for the ammonium ion. To test the ammonium ion, you add sodium hydroxide and warm it, and then test for the gas. Right, is it there? The answer is yes, it is. So observation is you are going to see the damp, the universal indicator paper, UI paper, will turn blue or purple. I bet they accept purple. In reality, it's forming ammonia, just to show you what's happening. The ammonium is reacting with the OH minus to form ammonia gas, which is an alkali, hence the blue, and water. And so there's the test we're going to see. That's the only observation. You don't see anything else. It's just a colorless solution. You don't see bubbles. You don't see anything. You just see the universal indicator turn blue or purple, and they'd probably accept either. Right, next. A student needs to find out the value of X in the formula, how much water there is. Right. So what they're going to do is they're going to take a sample of the solid, hydrated, and he's going to heat it. And that's going to evaporate the water. The water is going to evaporate, and of course, it's then just going to make its way out the tube. It's in an ice bath. The function of the ice bath is to cool down the gas so that it condenses, and then any leftover will go out there. So the hydrated, when reacted, goes to this. Okay. Calculate the mass of ammonium iron 3 sulfate produces, right, the mass of the test tube with the solid, right? So if I want to know the mass of that produced, I want to do that one minus that one. So on my calculator, I'm going to do 28.69 minus 22.04. I'm going to write it down because it's so easy that students do that without writing it down, and you'll miss that mark. Minus 22.04. Oh, I've done 1-4. So easy to do. 0.4. And I get 6.65 grams. 1 mark. Put it in the line. 6.65 grams. Next. Calculate the mass of water produced. Oh, that's more interesting. The difference between those two is going to be the water that's given off. The test tube won't change. So now we need to do 34.09 minus the dry mass water produced, what's left, minus 28.69, and that's going to be 5.4 grams. 5.4 grams. Next, calculate a value for X. So this is just empirical formulae. So we've got Cu, oh, right, come on. NH4 brackets 2 SO4 dot Fe2 brackets SO43. What a mess. Right, the mass of that was 6 points. The mass of water, H2O, was 5.4. Right, now remember, we need to count particles. The X in this formula is the number of particles This is one particle. Right there is a single, single particle right there. There is a single particle. And we want to count how many particles of water are attached to it. We need to count them. To count particles, we count moles. So give me a sec. My tablet's just sorting itself out. It always slows down as it goes on. It's because it gets hotter and hotter. Still trying. There we go. Right. Now that we've got those, I need moles. To get to moles, it's grams over rams. Number of moles is grams over the rams to get to moles. Right. Well, there's the grams and there's the MR. 532. Number of moles. 6.65 divided by 532. S to D. 0.0125. Next. 5.4 over 18. The MR of water. 5.4 divided by 18. And I get 0.3. Right, divide them all by the smallest. We're into empirical formula because we're going to have one of those, and this is going to be a much larger number. Let's try that. Divided by 0.0125. Oh, I've missed the 0. My calculator's not very good. 125. And I get, let's try that again. 0.3 divided by 0.0125. 24. Wow, that's really big. It's massive, in fact. That does make me worry. I'm not going to lie to you, it really does. But that's an enormous molecule. It's massive, and water's so tiny. This is going to have loads of water molecules trapped inside it. I do trust that answer. I think it sounds very reasonable. Next. It's not the end of the paper, I don't think. Oh, and that's the end of the paper. Okay, so I really would like, ideally, I'd quite like to check that all those answers. The problem is I'm not entirely sure where all of my paper, where my paper is. If I perhaps search for June. Laptop is really struggling. 2019. No, yes, 2019. I don't know what that's going to do. Might not work. The laptop's taking incredibly long to do all this. It should be there. I thought I would have downloaded it. But apparently I haven't. But maybe I have. Frozen. Question paper. That could be it. That one it? That's going to be the double award. That is the right paper. But the problem is it doesn't have the mark scheme attached. Of course it doesn't. Anyway, I think at that point, what I am going to do is go back. I don't know why it's gone and done that. I'm going to go back to this. Right. Okay, let's go hide, and I want to do go. There we go. Guys, thank you so much for coming along. I know that I'm not entirely sure whether or not the broadcast has been successful. I seem to be able to watch it, but as I said, I'm not too bothered. As long as you guys get to finish the paper, make sure you finish going through it. If you've got any questions, do let me know and come and see me with it. I will do paper 2 next week. And then the week after that, I'm going to go back to another paper 1. I'm going to go back to the previous one from 2018. I hope you found it useful. Keep working hard, Year 11. You're doing great. I'm super proud of you. I'll speak to you all soon. See you later, guys.